name's Hamish and I'm an instructor at RMIT Flight Training, and today we're going to be looking at the effects of controls. The aim of today's brief is to learn and understand the effects caused by manipulating the primary and ancillary aircraft controls. The application is used in all stages of flight. So before we start our actual effects of controls lesson, we need to understand what controls we're actually going to be manipulating. So first up, we have our ailerons. The ailerons are located on the outboard sections of the wings. And as you can see on the control column, highlighted in blue, we're going to manipulate the control columns by rolling them left and right. This will get the aircraft to turn to the left and turn to the right. The next set of controls we're going to look at manipulating is the elevator. Again, controlled by the control column highlighted in red. If you pull it back, the aircraft will start to climb. And if you push it forwards, the aircraft will start to descend. The next series of controls that we have are the rudder pedals, and this controls the rudder at the back of the aircraft. They're highlighted in yellow, so if you push your right foot forwards, that means the aircraft will turn to the right. And if you push your left foot forwards, that means the aircraft will yaw to the left. Definitions. So the first definition that we have is an aerofoil. The aerofoil is a cross-sectional shape of the wing. Now we also have a chord line which joins the leading edge to the trailing edge of the aerofoil. The leading edge of the aerofoil is located at the front, and you can think of it leading the aerofoil into the wind. At the back of the aerofoil is the trailing edge. An easy way to think of that is it's trailing behind the leading edge. Then the line that joins those 2 points together is called the chord line. Now we also have a definition called the relative airflow. The relative airflow is the motion between an aerofoil and the free stream airflow in front of it. It's always opposite to the aerofoil's motion. So our last definition is the angle of attack. The angle of attack is the angle between the relative airflow and the chord line. We can manipulate and change the angle of attack to either increase or decrease the amount of lift that we produce. The centre of gravity is the position through which the aircraft's total weight acts. And it always acts towards the centre of the earth. We also have the centre of pressure, which is a position on the aerofoil which the total lifting force produced by the aerofoil acts. The camber is the curvature of the aerofoil, and the mean camber is a line that gives an average picture of the aerofoil curvature. We also have static pressure and dynamic pressure. Static pressure and dynamic pressure are interrelated. The static pressure, which is felt from the weight of the atmosphere acting on an aircraft. So if you imagine a pool of water, and that pool of water is nice and calm, that's static. But if we then jump into that pool, that turns into dynamic pressure. Dynamic pressure is the extra pressure which is felt on an object in motion through the atmosphere. So you can think of it, if the car is stationary and you put your hand out the window, what you're feeling on your hand is static pressure. As that car starts to accelerate, what you're then feeling is the dynamic pressure on your hand. The principles of flight. So Bernoulli's theorem. Bernoulli was a Swiss physicist who created this theorem of how an aerofoil would work. Bernoulli stated that the total pressure of a fluid will remain constant when it's set in motion. And while that total pressure remains unchanged, the static pressure will decrease when there is an increase in the fluid velocity. Now we can consider the air as a fluid in the atmosphere. He also turned it into a formula. Pressure total equals pressure static plus pressure dynamic. Now what we have on the screen here is a Venturi tube. So it's a tube with a throat that narrows in the middle. Now you can think of the air that's flowing through that tube as a constant pressure or as the total pressure. Now before it reaches the Venturi, which is the constricting throat, the velocity and the pressure are equal. But in order to get the same amount of air or water from one side of the Venturi to the other side of the Venturi, two things have to happen, because we're still trying to get the same amount of water through that point. The velocity of that water has to increase, but at the same time when we increase the velocity of an object, the pressure will start to decrease. So once the water has gone through the Venturi, where the velocity is increased and the pressure is decreased, once it then exits the Venturi, the pressure and velocity will become equal. Another good way of thinking of it is when you're at class on the last day of term and it's really hot, and the last siren goes, everybody gets up and leaves, but to get through that door, everybody has to go through in a single file, which means the pressure decreases. You guys are going to start walking through a lot faster, and then on the other side of the door, the pressure and velocity are equal. This is how we generate lift. If we put an aerofoil into the Venturi tube over the top camber of the surface, the velocity will increase compared to the velocity travelling underneath the wing. When we increase the velocity on top of the camber or on top of the aerofoil, the pressure decreases, which means we're creating a low pressure system. Underneath we have a high pressure system, and we know that high always wants to go to low, and this is how we'll generate some lifting force to lift the wing off the ground and fly. The Coanda effect. This phenomena is where a jet flow will attach itself to the nearby surface and remains attached even when the surface curves away from the initial jet direction. A good way to describe the Coanda effect is with a teaspoon running under a stream of water from a tap. Now, it's very similar to Bernoulli's theorem in the fact that we're still analysing air as a fluid, and it has the same characters and dynamics. When we put that spoon into the water flow, the top surface of the spoon has a curve to it, very similar to an aerofoil. And what that curve does will increase the flow of water over the curved surface, and as we increase the fluid, the velocity, the pressure decreases. So as that pressure decreases, it will then create a low pressure system. On the other side of the spoon, there's a high pressure system. Combine these two together, it will then push the spoon into the flow, and the jet flow or the water flow will attach itself to the top surface of the spoon and keep it in that position. The lift equation. Don't be put off by looking at this equation. Once you break it down, it's very easy to understand. So we can use Bernoulli's theorem and the Coanda effect and create a lift formula which we can use as pilots to make our life a little bit easier. So lift is equal to the coefficient of lift times the half rho times v squared times the surface area of the wing. Now CL can be broken down into two components. It can be said that CL is equal to the camber of the wing combined with the angle of attack. The angle of attack is the angle between the relative airflow and the chord line. Half rho is the density of the air. V squared is the velocity, so that's how fast our aircraft is travelling. S is the surface area of the wing. But to keep things simple, we can use the pilot's lift formula. We can break those components down into the things that we can actually change as pilots. We can't change the density, and we can't change the surface area of the wing. So we can now say that lift is proportional to the angle of attack times the indicated airspeed.